Seems we are missing 6 of you. Let me wait another 1 minute before we start. How are you guys doing with the exam? Okay. Yeah, I think the average was pretty good. Most of you did pretty well. The average was like 86%, 43 out of 50, somewhere around there. And there were 2 of you got 50 out of 50, 100%, which is pretty amazing. Okay, seems we got more students coming, so let's go ahead and get started. Share my screen. Oops. Okay. So this class, if you look at the previous syllabus, it was irradiation, but later on I decided to replace it with the spray drying with some dehydration fundamentals, because we will have spray drying experiment in 2 weeks, and there was no lecture covering that topic. And also the syllabus was from the previous professor, and I had a feeling that the spray drying probably will be more important in your future career than the irradiation, because for a lot of nutraceuticals, vitamins, food ingredients, they're actually produced by spray drying quite a lot. And for irradiation, probably um, it's very less likely that you will have to deal with irradiation. So for that part, I think compared to spray drying is less important. And so that's why I decided to use spray drying here, talk about spray drying today, and I'll squeeze the irradiation with the microwave for the next into the next lecture. Okay, so before we start, just want to briefly uh, talk about the exam. It was pretty good. We had 86% of average, and 100% of 2 of you got the 100%. Okay, and then and this week we have 2 assignments due, the lab report 1 and assignment 2. So in the lab report 1, it's our first group lab report. Okay, so all the requirements have been addressed in the rubric. And if you have any other questions, let me know. So in your submission, please designate who is the group leader. Just mark the name, which will be easier for me to reach out to the groups if there's any issue. Okay, and also I will post a class survey to ask you for your feedbacks regarding the past 4.5 weeks of the class, and it will be a anonymous survey, and you'll receive 2 extra points by providing it. But right now I'm trying to figure out how to do it, because the survey itself is anonymous, but in the other hand, you receive extra points, which is not anonymous. So I'm trying to figure out a way to collect the information and also identify who provided the survey results. So yeah, I'm trying to figure that out right now. Okay. All right. So before we start, I want to so in our last week's class, Abby talked about after class. She mentioned about a packaging design that has been used in hot fill hold, which is sounds very interesting to me. And I was inviting her to share with the class about this very unique design. So Abby, if you're ready, I can share the screen. Let you share the screen so you can talk with us.
That'd be great.
Okay, okay, now you should be able to share the screen.
All right, so what I was telling Dr. Feng about is vacuum panels in PET bottles for hot fill hold processing. So PET bottles and hot fill, if you used a bottle that looked like this on the left, it would end up looking like what's on the right. It's a science experiment, but it's the best I could find on the internet for this type of um, deformation. So those bottles, when the vacuum is pulled, the weakest point is at the middle of the bottle. So the bottle kind of caves in and it looks bad. But people have designed bottles so they have vacuum panels is what they call them. So like a Gatorade bottle, say, has those panels on the side, and that's for when the um, package gets hot and then it cools down, it sucks in, and those vacuum panels are the weakest point in the design. And so they suck in at those points. So the bottle still looks good, but it really did deform, but just in the right spots. I think the bottom part of the bottle is also supposed to do that, but it doesn't do it enough. And so this also allows the processor to use lower amounts of PET and have a better structure to their bottle. So yeah, that's kind of the advantage of it. I don't know if that makes sense. Is that
Yeah,
I thought it was cool.
that's a really cool design. Basically, you just design where you want to deform, and then it actually deforms in a very uh, it's quite, it looks quite amazing because it looks much better than those plain cylinder shape, right? And
Mm-hmm.
also it holds more pressure against the vacuum.
Yeah.
Yeah, great. Thank you, Abby. You guys have any questions? Okay, great. So thank you, Abby, for sharing. I really appreciate that. So
Yeah.
in the future, if you guys have any ideas that you want to share, please, let me know. And then it'll be great for us to, share every ideas so we can learn from each other. Okay, so let's move forward. So since this class will be talking about the dehydration and spray drying, do you guys can you guys name a few of those products that uh, you found in the grocery store, either made by dehydration or spray drying products?
They do a lot of eggs with spray drying and also fruit, I would say.
Carly, you mean eggs, spray dried eggs?
Yeah.
Really? I never see that. Is that what's that used for? Is that food ingredient?
Yeah, I know that someone, I think Lauren is in this class, but she was working with spray dried eggs, like at
Nice.
Yeah, it was a pet food company. Well, they did ingredients for pet food, but they basically would just take like extra egg from the breakers and then spray dry them.
Nice. For pet food. Do you know if they are whole eggs or just egg white?
They did both.
Oh, nice. And that sounds pretty difficult because you think about how viscous that it is, right?
Yeah,
But
it I mean, I know it smelled terrible in summer, but it worked pretty well. I think they just blended it up and they had to like I know they did certain measurements to make sure there was a like balanced amount of egg whites and egg yolks.
nice. That sounds pretty exciting. Yeah. So like I said, the spray drying has been used quite a lot. I would say uh, 80, 90% of the food industry are using the spray drying to produce a lot of food ingredients, a lot of micro encapsulation. So those different applications. So egg spray dried egg, definitely something quite interesting sounds to me. And for pet foods, oh wow, a pet are eating pretty healthy right now. Okay, so great. So I also listed a few examples here, like beef jerkies, fruits, dried fruits like apples, grapes, raisin. So a lot of fruits, they can be dried. And also we have a lot of pet foods. So the milk powder is one of the spray dried sample, right? Because they form powder structure. Okay, so quite a lot of food products in the market are right now by dried, are produced by drying. Okay, so the reason, so this is a review. I assume that you guys have learned all of this in 204 and 330. So this is just a review to just to recall memory. So I'll go a little bit fast here. So if you have want me to slow down or any part has never been covered in previous courses, I will just stop and stop there and explain a bit. So the reason that we want to dry our food product is to extend the shelf life, right? Because from the standpoint of handling, storage, and transportation, the dried food will be more convenient to transport. And for example, if you go to the grocery store and buy a infant formula, probably it's dried, right? Because that can sustain, can feed the baby for months or even more time, longer time. But if you buy liquid infant formula, that probably can only last for a week or so. So dried foods definitely help us to transport food products more conveniently. Okay, and also a lot of ingredients, they are dried. For example, a lot of flavor ingredients like spices. So those stuff are also dried because we used them for a little small amount, okay? And also, if they are not dried, they probably cannot last for a long time. So those are a lot of all the reasons that we want to dry food ingredients or food products. So probably you guys are very familiar with um, this curve, right? This curve has been popping out again. Basically, the water activity is the key impact, in fact, key factor that influence all those chemical reactions like lipid oxidation, non-enzymatic browning, hydrolytic reaction, like basically enzymatic hydrolysis, right? Or sometimes chemical hydrolysis, and also enzymatic activity, and a lot of microbial growth, right? So when I was studying food chemistry, one of the questions I always get asked is that if we dry food, why do we keep it around 0.2 water activity? If we go to 0, then the lipid oxidation is going to be very rapid, right? I don't know if you guys still remember why the lipid oxidation kind of it's speeded up at the low water activity, guys. Just a small quiz for the chemistry class. You guys remember? Okay. All right. So
Can you repeat your question?
so if you look at this chart, you can see that the most reactions will be speed up while the water activity goes to higher level, right? For example, the microbial growth will start on around 0.8. I will be speeding up when the water activity close to 1. For example, enzymatic activity, if you look at the curve, the higher water activity, the faster the reaction, right? And also the browning process as well. But if you look at the lipid oxidation, the fattest rate is actually found when the water activity is close to zero. Do you know why? Why is that?
Is it because the air will get to the lipids and oxidize it if there's no water to prevent that? I don't know.
That's a good guess. Any other thoughts? Have you guys seen this curve, this chart from food chemistry class or other classes? Yes. Okay. Yeah. So let me explain, because I assume this chart keeps popping up and telling you the relationship between the food stability and the water activity. It's quite important for food science students. This chart kind of summarize, integrate all the knowledge that you have learned in the past 4 years. So so Abby gave a very good guess. She said that at water is close to zero, the air has more exposure to the food. That's one of the reason, I would say. And more likely is that the lipidization is kind of accelerated here because lipidization is highly, um, I would say, catalyst driven reaction. And when we have very low activity, water activity, the concentration of catalyst actually will be reaching to an extremely high level. For example, a lot of metals or transition metals, they play as those those catalysts during this process. Basically, if we think about the lipidization, it will generate a free radical, right? Because if you still recall, it's a chain reaction. So that's why that the free radicals can be easily created when we have less water, and also those without any water, those catalysts can easily accelerate this reaction. But if I want to go too deep, then it can be a one class topic talking about this. Why is that? But in our class, I want to explain a little bit about this topic is that when we are doing drying, we're actually lowering down the water activity from close to 1 to either zero point 0.4, zero point 0.3, right? But we never want to go to point uh, close to zero, because in that case, if we dry it too much, then we will accelerate the lipidization process to an extremely dangerous level. So that's why that's part of the reason that I want to ask you this question. That's because when we are doing drying, it's not like the drier the better. We have to stop somewhere to inhibit the lipid oxidation process. Okay. Otherwise, the rancidity will build up very quickly. All right, and for the reason of drying, actually, we have talked about a lot because we know that the supply chain of food is very long, right? From if we talk about from farming to all the way to the consumers, will go through the production, shipping, processing, packaging, storage, distribution, and consumption. So the drying can be involved in every single stage in this process. For example, from packaging to storage, we can, if we apply drying, we can easily reduce the cost during the supply chain of the food ingredients or food products. So it's mostly for the economic reasons. Okay. So there's a quick definition about food dehydration, assuming you guys learned it before. So basically, it's a unit of operation that removes water. So here is one thing that I want to mention is the the difference between dehydrated foods and the dried foods. So basically, if you have water, the water content lower than 2.5%, we'll call it dehydrated foods. Okay, and this water content is based on dry basis. You guys still remember what is dry basis? Wait. Okay. If you don't recall, I can explain a little bit more. I saw some of you nodding heads. Okay, so the dehydrated foods we have less than 5% water. For dried foods, we will have more than 2.5% water. So the definition of the regulation of dehydrated foods is a little bit more restricted compared to dried foods. Okay. And there are two ways of doing that. We have vaporization and sublimation, right? Vaporization is just we heat it up to remove water, and sublimation is that we directly convert water from ice to vapor by sublimation at very low temperature. Okay, so have you guys learned about this in previous classes? Or it's like brand new to you? Oh, okay, good. Okay, so that's all the refreshment about the dehydration. The reason that we do that because in spray drying we have to determine a lot of processing parameters. For example, we have to determine what is the airflow rate, the relative humidity of the air, and also how fast we can feed our food product into the spray drying system. So all of that they are basically a very conventional drying process. So it's kind of connected to the to the air drying. So that's kind of a recall of those old concepts. So now we'll be trying to analyze a spray drying system. Okay, so basically in a drying system, we have two inputs, right? We have the wet food input. Okay, sometimes it can be milk or coffee or sometimes soy milk. And on the other hand, we have another input that will be hot and dry air. Okay, so the m dot p is the flow rate of the food, and the WP1 is the water content of the wet food. And on the other hand, we have hot dry air, and the hot dry air will be fed at m dot zero, ma dot, which is the airflow rate, and WA1 is the water content in the dry air. So after drying, we have two outputs. The air will be cooled down and become humid, and the food will be dried, and the water content will be dropping. Okay. So because analyzing this system, we need to refresh a little bit about the psychrometric chart, because especially to determine the air property, it's quite important if you guys for you guys to determine what is the absolute humidity and those other values. So I want to very briefly go through this psychrometric chart just to refresh your mind. I think many of you have learned about this in 330 and 444. So psychrometric chart is used to study the interrelated properties of air, right? And basically we have 6 parameters. We have dry bulb temperature, wet bulb temperature, relative humidity, absolute humidity, specific volume, which is the density, right? And also the enthalpy, okay? All right, so for example, if we have this very busy psychrometric chart, we have dry bulb temperature at the bottom, right? We have the absolute humidity on the y-axis on the right side, and we have wet bulb temperature, okay? And also relative humidity on those curves. And those curves, they are specific volume, okay? And on this side, we have the enthalpy. So for example, if we let's solve, for example, if we have the smokehouse has wet bulb temperature 45 degrees C and dry bulb temperature for 51 degrees C, based on those two parameters, we can determine the rest of them, right? Because I know you guys have done a lot of those conversions in the past, so I'm just refreshing to those who are not, who might forget since it's been a long time. So for example, if we have 45 degrees C and 51 degrees C two temperatures, we can locate them, right, on the psychrometric chart. And then, so here you find the dry bulb temperature on the bottom, and on the left side you find the wet bulb temperature, right? And then you extend the line and find the intersection, and we have those curves showing the relative humidity, right? So based on that, we can reading those curves by approximation, we can find the relative humidity. And if you want to go with absolute humidity, you can draw a line to the right side and locate that number. Okay, let me know if you forget, and then I can probably slow down a little bit. Otherwise, I'll just keep quickly moving through. And then for the specific volume, you'll look at those lines on in the green lines. Okay, so and then it's also some approximation. Okay. So because a lot of case, for example, if you're working in the pilot plant, it's less likely that you'll bring such a psychrometric chart all the time, right? So so a lot of case, if you are asked to solve a technical question very quickly, you might need to, and if you need to find that psychrometric chart, it's not realistic. So there are actually a lot of online psychrometric chart toolbox, which will allow you to get all those values in 1 second. For example, here I posted one link, is the psychrometric toolbox. Let me pull it out here. Okay. So for example, if you type in, for example, we had 45 degrees C for the dry bulb temperature, and then we had 51 for the wet bulb temperature, and we just simply click the calculate, and then you get all those values that you needed, which is just 1 second, and you can get all the values very accurately. So this is one way that I would recommend you, especially if you are very familiar with this chart. It's just easier for you to get all those values in the real life. All right, so now we can come back to our drawing system. So basically, because a lot of case, as I mentioned, we trying to design a spray drying system, but we don't know uh, how fast our airflow can go, what is our drying capacity is. So in that case, we need some information from the dry air. So let's do a quick practice for this problem, and then we'll talk about how to solve it. So basically, we have a cabinet dryer. Okay, it's used to dry food product from 68 moisture content dry basis to 5.5% moisture content in dry basis at 100 kilogram per hour. And the drying air enters the system at 54 degrees C and 10% of relative humidity, and leaves at 30 degrees C and 70% relative humidity. And the question is that what is the airflow rate that we need to supply this drying system? So here I use the cabinet dryer, but if you use a spray dryer, it will be the same question because they're basically the same principles. Okay, so I'll give you guys about 2 minutes to think about this. Okay, so after that, let's talk about how to approach this question and then share the answers. Okay. Okay, so I'm giving you all the variables here. It might be easier for you to think about it. Okay, you can let me know if you have finished, or either in chat box, or send some um, a reaction face will be, either way will work. Just let me know when you guys finish. Anyone wants to share? Not necessarily the final answer, but how you solve this step by step. What is your thought process?
I mean, first is first, we have to make a mass balance. So what goes in must come out.
Right. And then for the air, do you use the relative humidity or do you use the absolute humidity? Any thoughts here? Okay. Uh, was this covered in 444 and 330? Is covered? Okay. Um, okay. So probably I will, list because when we, the reason that I want to refresh this part is that when I talk about the next a few slides about the details about spray drying, those fundamentals, um, especially for the spray drying system, is so delicate that our airflow rate is the key point that, and the airflow and air properties that our input air, sometimes we need to add a humidity dehumidifier, sometimes we need to heat up to extremely high temperature. So those are very critical and delicate to the product. So the reason that I want to refresh about a little bit of the calculation that you'll find later that if we don't supply enough air and if you don't supply enough, the air is not dry enough, our final product will be caking and aggregate. For example, if you receive a milk powder that is um, aggregated, then because it's made for instant dissolution, and if the spray drying process is not complete, or it's too dried, then either way will cause a lot of issues. So the processing control, the parameter optimization is one of the key factors when we're designing a spray drying system. So that's why I'm bringing back all those stuff, just try for you to refresh the mind, especially how to use the psychrometric information to solve this problem. Okay, so let's look at the solution together. So actually the first step, as I always do, is to write down the governing equation. Basically, it's a very simple mass balance equation, right? We have a lot of knowns and some unknowns, right? If we look at this equation, we have the um, the water comes in, right? If you multiply those, water comes in and equals to the water goes out, right? So what we know is that we know the all those um, all those values, but we what we don't know is the MA, which is the dry hot air flow rate. But for the rest of them, we basically know. But one thing that we need to convert is that for the air property, we know the relative humidity, right? Which is 54 degrees C and 10% of relative humidity. But we need to convert that into absolute humidity because when we are working on mass balance, everything is mass based. So absolute humidity is a mass-based value, right? So once we convert the air in, the relative humidity into the to absolute humidity, we will get 0.0094 kilogram per kilogram air. You guys can use the link that I posted in the last slide to very quickly get that number, okay? And then once we get those absolute humidity numbers, we can plug them in. And then the only unknown variable here is the airflow rate. And then we can solve this airflow rate that is required. So here you can see we need at least 6,093.5 kilogram per hour of the air to make sure that our food product is dried to our desirable range. So that's the very basic way of solving the required airflow rate problem. Okay. So do you guys have any questions about um, the procedures to find the airflow rate required? Or if or let me know if I if I move too fast because I'm not quite sure how well you still remember this everything here. Any questions? Or give me maybe a smile face if you are okay with this part. Okay, great, great. All right, so I will skip the this problem. Basically, I think you guys are pretty clear about how the air interacts with foods and how all the mass balance happens. So today I will probably focusing more on the food property and the dynamics of the water loss during the drying process. So basically everything that we talked about before, they are all external conditions. For example, air temperature, the relative humidity, and air velocity. They're all external factors that we controlling the system. But on the other hand, we also have quite a lot of internal factors. For example, the food property, the intrinsic properties of food, okay? So this is something that we want to talk about today. Okay, so in the food matrix, for example, uh, like milk powders or dried cheese powders, we have different components, right? So first of all, we have a lot of surface water, and then we have bulk water. On the other, within those solids, for example, milk powder solids, they're even bond water, which means those water are very um, highly they bond very tightly to the food molecule, and we can hardly remove them during the dehydration. Okay, so and also we of course we have some air bubbles. So my question is that among those water, which one do you think will affect the water activity here? If we talk about a food has high water activity, do you think we have a lot of surface water or a lot of free moving water or the amount of total water?
Free moving water.
Good, Julia. So the free moving water determines how how much our water activity goes, basically how active the water can move within the fluid matrix. Good job. And remember that free moving water includes both surface water and also bulk water, okay? All right. So if we think about a drying process, we're actually reducing the water from very high level to almost nothing, right? So if we plot out a moisture content curve against the time, we'll have three stages during the declining of the water content, right? So at the very beginning, we have kind of a lagging time, and then we will have a linear dropping curve. And then finally, the decline of the water, the water content will be slowing down. Okay, so we have basically have three stages. Okay. Have you guys learned about this before? Okay, great, good. So I'm going to move very fast here as you guys are quite familiar with this. Okay, so basically we have drying and drying rate. Okay, and here we have critical moisture content, right? So everything. So here we need to convert the drying rate, drying curve from those moisture versus time to the drying rate versus uh, the dry base moisture content, right? So basically it is the water versus the solid content, X value. And by looking at this curve, we can get the critical moisture content and the equilibrium moisture content. So there are three stages drying, right? The initial drying concept and then the constant drying period. And finally, the drying will be slowing down, right? Finally to the falling rate drying period. So three stages, okay? And afterwards, we have the second falling drying rate. Basically, we're trying very hard to remove the bound water, but typically we cannot remove all the bound water here. Okay, so when we're talking about the spray drying, typically the second falling rate period will not happen. We typically stop at somewhere close to the falling rate period. Okay. All right. So these are two critical values. I assume you guys have learned about it before. Okay, so I'm going to skip everything here, and let me skip to the spray drying. Okay, so this is the slide number 41. Okay, we'll start from here. So if we talk about drying, there are a lot of drying technologies, right? If you're not familiar, forget about all the drying process. You can go back to my previous slides comparing all the drying and how they, how the product compare to each other. Okay, so here let me talk about the drying the technology of drying that is evolving in the past few years. So at the very beginning, our drying is actually a hot air drying. So for example, we even in hundreds of years ago, people have been using the hot air drying or sun drying to dry their foods. And so to extend the shelf life of the foods or to keep it longer time. And then later on, about 50, 60 years ago, the spray drying and the drum drying um, has been invented. And then very recently, about 30, 40 years ago, we have started using freeze drying, which is super expensive, but the product quality is just superb, right? And even now we have started using freeze drying in those pet foods, but they are sold quite expensively. And also we have osmotic drying, dehydration, right? So basically using the osmotic pressure difference to extract the food. So those are the third generation of food drying process. And now we're using a lot of fourth generation. So the fourth generation, we have been applying a lot of electromagnetic waves. For example, microwave, we'll talk about next class, okay? And the radio frequency, and then sometimes the refractance window. So but basically it's a very short period um, uh, of the uh, of the radio of the uh, electromagnetic wave treatment. Okay, so the fourth generation basically were combining different technology together to accelerate the drying process. So if you think about the hot air drying, it might take hours and days to reach the low water activity, right? But in the second generation, the drying can be shortened to a few seconds, right? For example, spray drying, we can do everything within 10 seconds. But the problem is that we can only process powder products, right? That's a limitation. So to overcome that, we actually developed the other technology to treat those bulk food products, and they can still be dried very fastly. So those are all the reason that we are still advancing our drying technology, although it's a quite old um, processing. And now the trend is going more sustainable. For example, can we use less energy, right? Um, and also how can we apply those drying technology to those countries that is lack of gas or steam supply, or how can we um, dry food in a home-based setup within a very short period of time. So those are the modernization of drying technology. So it's still evolving, and we still see a lot of companies investing in this area. And one thing that I noticed that is one company spent 5 years to develop a room temperature spray dryer. Basically, no heating is required, but everything, the milk powder can be dried in room temperature by spray drying. So in that case, we actually have no heat denaturation of the protein, and also there will be no vitamin loss or other beta carotene loss during the spray drying process. So that company was acquired by ADM. I think it was last year for hundreds of millions of dollars, and because they spent many years developing this technology. So you can see this area is still evolving very actively, because drying is still playing such an important role in our daily life. Okay, so when we talk about the spray drying system, I think you guys have seen this chart before. So a spray dryer, the one that in our pilot plant is also very similar to this one. Basically, we have a feeding tank, okay, and then we have a pump that will be transporting our food product to the top, and they will spray through a nozzle automation, okay. And in the meanwhile, we have the air to dry the food. So the air will be heated up. So the reason you guys have seen the psychrometric chart, right? The heat air has lower relative humidity. So in that case, we can carry out more. We can carry more moisture from the food, make sure that food is more dried. So that's why we need to heat up air. Okay, and the air and the food product will be mixed at the top, and then the food product will be dried, and then we have a cyclone to separate the air and the food product. Basically, this is a condensing part. You will see the air is cycling around in this collector, and those powders, because the density is a little bit higher, so it will settle down to the bottom, and the air will be exhausted through this fan. So this is a kind of separator. If we don't use this separator, the air will take out a lot of powders, and we'll lose a lot of products. Okay, so the one that in our pilot plant is very similar to this one. Okay, so you'll see in I think it will be in 2 weeks. So here's a video I want to share with you about how a typical spray dryer works. Okay. Let me share the sound.
Heat air enters into the drying tower uniformly through the spiral case and hot air distributor. The liquid is fed into the atomizer by the liquid feeding pump and then is atomized into very fine bits. The bits will be dried into powder very fast when they contact hot air directly and follow in parallel. The powder products should be collected at the bottom of the drying tower and cyclone. Sometimes also the closed back filter or wet scrubber. The air should be exhausted into the air in normal process. Features and applications. 1. Fast drying speed. The surface area is increased greatly when the liquid is atomized, and the water should be evaporated instantly in the hot air. 2. Applicable for drying heat-sensitive material. The beads flows in the same direction with the hot air. The air with high temperature contacts only the beads, and then the temperature drops down very fast. The dry products contacts only the low temperature air. So the process is applicable for heat-sensitive material. 3. The application range is wide. It might work as hot air drying or cool air congelation according to the property of material. The most common application includes drying of milk, fruit juice, dyestuff, pigment, pesticide, byproducts in slaughterhouse, blood and blood products, detergent, surface active agent, fertilizer, and instant food, etc. 4. The drying process is finished very fast. The product keeps bead-like. The flowability and solubility is good. 5. The process is simple and the operation is easy. It is normally applicable for the liquid with moisture content of 40 to 80%, and for some special material, it can be dried into powder directly with moisture content is up to 90%. Screening and grinding process are normally not required for this process, so the process is simple. The size of product, bulk density and final moisture content might be adjusted in a range. 6. All parts that contains materials are constructed of stainless steel, so to avoid pollution of product. 7. Siemens PLC and human-machine interface for operation system. Fully automatic operation might be supplied on request.
Okay, so this is a very typical drying system that you will find in a lot of production lines. So if we break it down, you'll see that we have a drying tank, drying chamber. Basically, the air and the food will mix in this giant chamber. Okay, in our case, it's not that big, but it's quite large. So the cleaning sometimes will be taking some time because if we were producing milk powders, those milk powder kind of stick on the walls, so it's quite difficult for us to remove them. And the number 2 here is the air heater. Basically, we're trying to reduce the relative humidity of the air by heating it up. And sometimes if it's a bad day that the air is too humid or it's a rainy day, we have to connect it with a air dehumidifier. Basically, because otherwise, if we keep supplying humid air into the chamber, then our product can be hardly dried. Or a lot of cases, for example, in San Luis Obispo, we have the humidity in the air varies quite a lot. We have very dry days and sometimes we have very humid days. So if we don't have a humidifier, we'll get quite different results day by day in the daily production, because as you did all the calculation, the extent of the drying is pretty much depending on the air properties that we are supplying. So if we don't have dehumidifier, we have to make a daily adjustment on those parameters to make sure that our food product meets the same quality from everyday's production, right? So that's the air heater. Okay. And the number 3 is a milk concentration tank. Okay, so basically this feeding tank, right? So every time when we talk about spray drying, we need to pre-concentrate our milk, because the spray drying can only deal with concentrated milk products. If it's too dilute, then the drying process will not be able to remove all the water to produce powder. So that's kind of will lose some energy, waste some energy, or we have to process at a very low feeding rate. Okay, and the number 4 is a high pressure pump. Basically, we're pumping the milk from the tank into the drying chamber. And number 5 is atomizer. In the atomizer, basically we're spraying the milk into the drying chamber, right? And sometimes we connect the atomizer with a high pressure nitrogen, because, for example, if we process something like milk or the egg you guys mentioned before, it's quite viscous. So during the process, it's very likely that our product will clog the channel. So in that case, the process will be shut down. So a lot of cases we use the high pressure air or nitrogen, just try to keep the liquid flow smoothly here to avoid any kind of clogging happening. And then in number 6, you can see there's a main cyclone. So in this cyclone, we are separating the powder and the air. The air will go out from the number 8. Okay, we have the air suction. Basically, it's a vacuum and a filter. Okay, if we don't have a filter, then probably we're contaminating the air by those powders, and that can be quite dangerous. If the air powder is accumulating in the air, then probably it'll cause some explosion, or if you and also it damages humans' respiration system, right? So this is air filter in number 8. And sometimes we connect it to a secondary cyclone to better separate our food product, okay? So this is a complete design of a spray dryer. So in our pilot plant, we have a very similar design to this one. But our tank, feeding tank is connected, right connected to the to the uh, to the spray dryer, so it's not far from there. But in a pilot plant, because the tank is huge, and there's no way that we can attach the tank on the main chamber. So sometimes we need a long pipe to transport it. All right, so the spray drying process is pretty much like the typical drying process we talk about. And also it has 3 or 4 stages here. So the first step for the spray drying is that the temperature on the surface of the powder will be increased to reach equilibrium temperature. Okay, so basically the temperature will be increased to a certain level that the evaporation can start occurring. Okay, so the 0 to 1 is the temperature rise, and 1 to 2. So this curve is temperature versus drying time. So it's not doing anything with the dropping of the moisture content. So from 1 to 2 in the spray drying, there's a constant temperature range. Basically, the moisture from the surface will be evaporated, okay, and the moisture from inside will be moving to the surface. So that's why you see the temperature is constant. And then because all the latent heat is absorbing all the energy from the air, and it causes a minimal increase of temperature to the droplet. And once all the surface water has been removed, the drying rate kind of decreases, which means our latent heat is not absorbing enough heat. That's why that our the droplet has to increase temperature to compromise that part of energy. And then you'll see the temperature increases. And then to a certain level that we have shrinkage occurring because the inside becomes porous, and the solid is no longer able to hold its structure. And so it kind of collapse. The structural collapse causes the shrinkage. Okay. All right, and finally we have the last period. Basically, it's almost finishing up, and we only have the sensible heating period. Okay, so this is for spray drying temperature curve change, and a lot of the case the shrinkage is one of the key point because a lot of particles they have different gas transition temperature, right? Especially with the water. With the water content high, then this gas transition temperature is pretty low, which means it can deform easily at a low temperature. So in that case, we'll have the particles being highly wrinkled instead of spherical. So if we take a microstructure of those wrinkled particles, you'll see that none of them looks like a perfectly sphere, but they all have kind of defects on the surface. That's all happening during the shrinkage period. Okay, so we have 3 periods, just as we talked about. Okay, so atomization is another thing that we just talked about. We have 2 types of atomizer. We have rotary atomizer, basically it's a wheel that is spinning those liquids into the air. And also we have pressure nozzle. Okay, basically we use high pressure of air to push the liquid. So those are all the different designs of the rotary atomizer. So nozzle is one of the key points in our spray drying system because the nozzle design, a lot of case, it determines how well that we can dry our foods. So the most common nozzle you can see here is the two-fluid nozzle. So two-fluid nozzle means we have 2 types channels. The first channel is the liquid feed, and on the outside we have the air channel that is surrounding the liquid feed, so that they can mix pretty well to create to expose the liquid to the air in a maximal way. And sometimes we even induce compressed air, that is to helping to increase the air pressure so that the clogging will be less likely to happen. So if you see sometimes there's a noise, typically uh, by the pressurized air, that means the system is more resilient against those clogging problem. Okay. And more recently, we have seen the straight fluid nozzle being very, very popular. That is because I don't know if you guys learned about the microencapsulation. So a lot of companies on the food ingredients, they are now produced in a encapsulated way because, for example, if we talk about vitamins, typically you don't want the vitamins to be uh, just pure vitamin, because those vitamins can be destroyed during the gastrointestinal period, right? Because if we consume a vitamin just by oil droplet, then when it is passing through the gastric phase, the low pH, everything can can lower down the bioavailability of those food ingredients. So for those vitamins, we want them to release a little bit slower, and we want to have something to protect it. So in so that's why sometimes we need a free fluid nozzle for the purpose of creating a core shell structure. And this is something that we see ingredient and carry those food ingredient giants. They're heavily investing this area. And I was also working on one of their free fluid nozzle project to produce those oligosaccharides. Basically, it's for the targeted delivery. If you think about flavor compounds, oligosaccharides, beta carotene, they need to be delivered into different parts in our human body, right? For example, flavor compounds, we need a very rapid release into the mouth within 10 seconds after consumption. Otherwise, if you swallow it, the flavor compounds it's no longer taking any effect. But however, for oligosaccharides, we need to deliver them all the way to the colon because they are feeding the gut microbiota, as a prebiotics, right? And for some vitamins, we are trying to feed them into small intestine, right? Because that's where that they are absorbed. So that's why that we are those companies, they're trying very hard to design the three-foot nozzle so they can create a core shell structure. So the shell will be the control release raw material to help our target delivery tasks. Okay. But if we use a very conventional two-foot nozzle, then the, the product that we're producing is kind of a mixture of the raw material and the core material. Okay, is that clear, guys? Okay, so this is one of the trend of the industry in the spray drying field. Okay, so these are the comparison of the particle size made by different nozzles. So basically, if you look at the rotary wheel nozzle, it's on the very left one, and then you can see the particle size distribution is very wide, from 1 micron to 600 micron. So because the rotary wheel is not it's not distributing those droplets very equivalently to the drain chamber, but instead, so that's why you see a big variety of droplet size. So in spray dried products, droplet size actually provides a very critical role because, for example, if you think about a powder product, if the particle size is too small, what will happen? You guys think if you have a very, very tiny particle size? Okay, so probably I can, so think about if you have a very tiny powders, they tend to be blown away by the air, right? They kind of flow in the air, and for example, when you open an infant formula tank, then all the powder just escape to the room, which is sometimes it's not good, right? And on the other hand, if we have the particle size very large, what will happen? Any thoughts?
Possibly the middle won't get dry and it won't rehydrate, if that's what you're trying to do with it.
Yes, yes, good job, Abby. So if we have very big chunks, you can think about, because a lot of spray dry foods, we're trying to make instant coffees or instant soluble infant formulas. And then we'll assume that we have to take minutes of 5 minutes to try to stir our instant coffee to make it complete soluble. That's probably not a good product, right? So neither we want neither small particle nor large particle will be good in this case. So we want to control or confine our droplet size or particle size into a very small range, and that range, the particle can be free moving, right? And it can, but it on the other hand, it's not too big to take a long time to dissolve. So from this figure, you can see that the two-foot nozzle is much better than the rotary wheel nozzle and the pressure nozzle in terms of controlling the size range. Okay. So that's one of the concern that we have to think about in those atomizer. But the problem is that the efficiency of the two-foot nozzle is not as good as pressure nozzle, because by supplying more air, we are actually accelerating the drying process. So the airflow is, let me see if we have time. So I'll quickly finish here. because we covered quite a lot of content in this lecture. So airflow, just like in the heat exchanger, we have different ways of supply air and mixing them with the food product. We have the cold current flow, constant current flow, and the mixed flow. So in the cold current flow, basically the air is supplied in the same from the same spot of the food product, and they will flow the same direction. And the constant current flow that we will, in that case, will supply the air from the bottom of the chamber. And mixed flow is just more like a vertical, perpendicular mixing. So those are three ways. And sometimes it's hard to determine which one's better than the other. And also once the system is already set up, it's hard for us to re to read to process food with a different airflow, because the air inlet has been fixed in a certain location. So before we design a food system, we need to use something called a simulation tool to kind of predict in this chamber geometry which airflow rate, which airflow direction is more optimal. So basically, if you so this figure is created by a simulation tool. A lot of cases we use partial differential equation based on COMSOL. So basically, it's in a when you are designing this chamber, you basically draw a very nice geometry that is almost mimicking the real world chamber. And then we apply some air condition on the top and also food product condition. And also we input the air condition. Then by adjusting those parameters, we can easily get a distribution of moisture content distribution, particle size distribution, and also the temperature distribution in the chamber. So this is sometimes how we use simulation to optimize this spray drying system. So if you guys are interested in this topic, I can certainly introduce more about how the simulation tool helps us to better design a food process. But I guess this class will not allow me to fully teach you how to use this tool because this topic itself can be another course. But I will just briefly let you know how the simulation helps us better design the system, and also how to interpret those heat maps. And based on those simulation results, how can we adjust our parameters? For example, one practical application that if we are drying food in different air temperature, different weather condition, and we don't have an air dehumidifier, how can we adjust our heating temperature and airflow rate to reach the same product quality in a daily production? So this is one of the application, very practical things. Okay, so those are all the different flow patterns. Okay, so like just like airflow, we can feed the air from the top, we can feed the air from the bottom, and even for the fluid feed, we can also feed the fluid from the bottom. So really depends on which one is more efficient and what is the food property looks like. And all those different designs, we cannot say which one is better than the other, because everything has to be dependent on how well the system works. So that's why sometimes we also use those simulation, a lot of cases with COMSOL determining which geometry design or which flow pattern where we place the fluid will be the best case scenario. Okay. So, okay, I'm going to skip all this. So those are all different designs of the spray dryer because we are running out of time, and also they are quite, if you guys look at the slides, you'll be able to get it. So that's it for today's class. Actually, it's a lot of slides. And really, I will, in the exam, I will specify which of the slides are focused on for this class, because if you look at the slides, a lot of them are trying to refresh your mind from previous previous classes. Okay, so that's it for today, and we don't have lab this week. Okay, so but make sure that you turn in that 2 assignments, just a reminder. Okay, the assignment and the lab report. And also, so Kristen just shared me one idea how to do the anonymous survey, but still giving you the actual points. Okay, so basically, I will let you guys do a screenshot of those feedback submission and use that to trade for your extra points. All right. So I'll post that survey probably by the end of today, and then let you guys know. So please provide any feedback, either positive or negative, how we can improve this class to better, teach, give you all the class content more efficiently. Okay. So that's it for the class, and I'll see you guys next week.
Thank you.
Thank you.